Okay, so we're going to be talking about entities, components, and systems, and the Vec2 class. So ECS game programming. Why do we want to use ECS for games? There's a few slides that we've already seen before, but they'll go through pretty quickly. Just as a quick recap, ECS stands for Entities, Components, and Systems. Excuse me. Where an entity is any object in the game. So for example, the player is an entity, a tile is an entity, a tree is an entity, basically anything you can see, and even some things that you can't see in the game are going to be entities. And ECS is not specific to games. It can be used in any programming environment, but it is particularly well suited for games because of their dynamic and compositional nature. And so this is actually a software design paradigm, but of course we're going to have another brief overview of object-oriented design first. And so just some important notes before I get started. Large AAA games can and have been made with object-oriented design and absolutely no ECS. It's fine. You do not have to make the games this way, but in my opinion, at least for the small to medium-sized games that we'll be making and you might be making for your project, I think it's pretty nice. And I've decided to teach ECS for a couple of reasons. First of all, because in my opinion, it's probably better for the course, and it allows us to do like a lot of really cool things in the game really, really easily. And so that's why I want to teach it. And also not only that, because you may not have been introduced to compositional-based programming before, and I think it's something cool to learn, so you can use it in other areas as well. So some agree with using ECS, some agree with object-oriented design, or at least what I call object-oriented design. Neither one of them, there's no mathematical proof that you can write down that one is better than the other, right? So if you go to some game programming or game design companies, they might use ECS or something like it. If you go to others, they may say it's the worst thing in the world, right? So just to let you know, ECS is not the only way to do something, but it is the way that I want to do it in this course. And hopefully by the end of the course, you'll see the merits of doing it this way. So in object-oriented programming and object-oriented design, why we do that is that it helps us manage the data and the code. So if we were doing a pure object-oriented way of programming a game like this, then an entity would be any object in the game, and so we would use entity as the base class to store the things that are common to all of the entities. So for example, one of the things that might be common to all the entities is a position. Like this thing actually has to live in the world somewhere, so maybe our entity base class would just store a position, for example. And then tile would be another, tile would be a derived class, player would be a derived class, and they would all inherit from that base class of entity, or maybe some other class would inherit from entity and then they would inherit from those things. So you get this really nice hierarchical design. You know, some people out there love hierarchies of inheritance, some people hate them. I think that there are places for them and places where you wouldn't want to use them, but this is what we would get if we implemented something like this for game programming, right? So we would have an entity up here, sort of the top level base class, and then say, for example, we have some entities in the game that do move and some of them that don't move. So maybe over here you would have the dynamic entities that move around, so they would have something like a velocity, an acceleration, something like that, whereas the static ones wouldn't necessarily have velocity or acceleration. So the things that don't move in the game, you know, they would inherit from static, and the things that do move in the game, they would inherit from dynamic. And then you see this sort of cherry-picked example here where this can kind of be a little bit annoying when if you have this thing which is maybe static, but also acts as an enemy, then, you know, how do you do this multiple inheritance? It gets a little bit tricky. So it can be messy, and in the end, what you would probably end up with is, you know, if you have a game, you know, maybe you're making the 2D version of Elden Ring or something like that, you have 100 or 200 different enemies in the game, so you have 200 different classes, and it's just kind of annoying to manage all of that. In the entity component architecture, you would have an entity as any object in the game, and then you would just have these component properties that you can attach to entities or detach from entities whenever you want. So for example, some of the components you could have might be a position, a speed, a bounding box for collisions, health, weapon, damage, etc. So anything that, if you write up a sort of a game design document, anything that you say an entity can do will probably have some sort of component that is related to that thing. So for example, you could say, okay, the player jumps, but then it also falls back down because of gravity. So maybe you have an input component or a controller component for the player, and then, okay, he's going to fall back down, so maybe you would have a gravity component or something like that. And you can build your entities out of all of these components without having to have, like, 1,000 different classes in your code base. So what you get in the end is a much more flat structure where you just have different entities that you would want to construct, for example, a tree or an enemy and a player, and then you choose from this library of components that you've created in order to construct these entities. So for example, okay, what does a tree do? A tree kind of stands around, and it might have a sprite associated with it. So you got to be able to draw the tree, and the tree exists at a particular location. So what we would do, we would take the tree entity, and we would attach a position component, and we would attach a sprite component. And that may be all that it needs, right? So it can be drawn, and it can live somewhere. An arbitrary enemy, on the other hand, might have a position, it might have an AI that controls it, a sprite that it needs to draw, a bounding box, a velocity, etc. And then the player would be kind of very similar to an enemy, except instead of having an AI component, you would actually have an input component where the user's input is somehow controlling the player. So you can see this is pretty intuitive, right? We just take the building blocks that we need and we build up the entity from that. So ECS uses this composition-based design. We compose things out of components. And a component is essentially just properties that we attach to entities. And in this version of ECS that I'm teaching for this course, components are just going to be pure data. Okay, so if you look at some ECS architectures and implementations, some of the components will have logic directly attached to the component. So for example, if you have a gravity component, there may be a function inside that component that actually updates the entity to make it fall back down to the ground or something like that. But in our ECS, what we're going to do is our components are just pure data. So a gravity component might just be, negative 9.8. That would be the amount that, 9.8 meters per second squared that you fall whenever you're up in the air. So we're just going to use them as pure data. And then the things that will actually be doing the work are these systems. And a system, you can just think of a system as a function that does something very related to one part of the gameplay mechanics. So the systems are the code and logic that drive the behavior. For example, you could have a movement system, a rendering system, a sound system, physics system, etc., etc. So we can break that up really nicely. And what this does is it not only makes it easier to program, in my opinion, but also much easier to debug. So for example, if you have a system that does movement, if you have a system that does rendering or sound, maybe what we want to do is, okay, my program or my game is only running at like 30 frames per second. Why is that? Well, let me turn off the rendering and just run the physics system and see if the physics system is the bottleneck, right? So you can do all sorts of cool stuff like that. So here are just some examples of different entities you might want to construct and the types of components that you may want to attach to them, right? So we talked about player and enemy. What would a bullet have? Well, a bullet would have to have a position, a speed, an angle. Maybe the bullet is traveling at an angle like it will in assignment 2, a bounding box, a sprite that gets drawn, an amount of damage that the bullet deals. So you could attach a damage component, as well as maybe a lifespan component. So something we'll be talking about in assignment 2 is this idea of a lifespan, where I might say, okay, let's say my game is running at 60 frames per second. Whenever I shoot a bullet, if it doesn't hit something, I don't want it to just travel infinitely forever and always be taking up that memory. So maybe 2 seconds after I shoot a bullet, I would want it to disappear. So all I would have to do there is just attach this lifespan component, say, hey, I want this bullet to survive for 120 frames, and then the lifespan system would keep track of that, and anything that has a lifespan that has ticked down to its expiration date will just automatically be deleted. We'll see how that works in a couple lectures. And just another important note is that this is not the only way to implement ECS. This architecture, again, it's a balance between efficiency, ease of use, and ease of learning for undergrad students, right? If I was trying to talk to, not that I would, but if I ever gave, a talk like this or a lecture like this to AAA game programmers with 10 years of experience, well, I wouldn't because they have more experience than I do, but I would probably do it a little bit, more on the efficiency route rather than the balanced route. And so what I'm going to do is pretty much with everything in this class, we're going to introduce the way that we're going to do it for maybe the first assignment or the second assignment, and then each subsequent assignment, and in the end, we're going to have some lectures that aren't relevant to the assignments. We'll talk about, hey, if I was actually going to implement this in the most efficient way possible, what changes would we make, right? Is that entity design that we looked at in the first class, is that going to be really the most efficient way of doing it? Maybe I would want to talk about memory pooling or all these different ways that I can do things if I was then to go and make a more efficient game. So we're going to leave some of the optimization toward the end of the course. And again, none of this is the only way that you can do it. None of this will be the absolute bare metal, bit meddling type of most possibly efficient way to do things. But I will talk about that a bit later as it goes on. So what are some example systems that we may be dealing with? One might be a movement system, right? So how would we implement a movement system? Well, for every entity that I have in my collection of entities, take the speed and add it to the position, right? That's all you have to do. And now every single entity in your world has had its position updated based on its speed. It's pretty easy to do. A collision system. So let's say, for example, we have a function which takes in two entities and decides whether or not they have collided. And we'll be making that in a few lectures. So what we could do is say, okay, two things that are going to be colliding in my game are going to be bullets and enemies, right? Because if the bullet hits the enemy, we want to deal damage to it. So if we loop over all the bullets and then loop over all the enemies for each bullet, if there's a collision between them, take the damage of the bullet and subtract that from the enemy's health, and then maybe destroy the bullet. Or if we wanted the bullet to be able to pierce through multiple entities, we could give it some piercing component and then say, okay, this bullet, you've got a power up so the bullet will travel through 2 enemies and hit 3 total enemies. So whenever it hits something, you could subtract one of those pierces left, and it's actually like really easy to implement all these different types of mechanics. And then a rendering system, in practice, your rendering system is going to be a little bit more complex than this, but you could just say for each entity, draw to the window the sprite of that entity at the position of that entity. Right? So this isn't the exact code. It's not exactly how it's going to look. This is a more abstract view, but now you can get just a bit more of a view of what these systems are going to look like. And the overall architecture that we're going to be creating in this course by, assignment 3 or 4 is we're going to have a game engine. The game engine class will sort of oversee all the data. It will store all the assets and the sound and stuff. It will manage the different scenes that we have. Each of those scenes is going to be something like, okay, there's a main menu scene. There's an options scene. There might be a world map scene where I'm walking around to choose my level. There might be a battle scene if I was playing an RPG or whatever. Each of these scenes are going to have different systems because, of course, the menu, if I press up, down, left, or right on the menu, that's going to have a different effect than if I do that in the battle, right? So these are going to have their own systems that each handle inputs differently, rendering differently, etc. Each scene is going to have its own entities. So in the next lecture, we're actually going to talk about this thing called an entity manager, and that will really nicely handle all of our entity memory management and lifetime and all that kind of thing. I think after you see that lecture, or after you use the entity manager in assignment 2, you'll never want to do anything else but have an entity manager whenever you create games. It's really, really nice. The entity manager is going to store entities, and the entities are going to store components somehow. So that's going to be the basic architecture. There's no multi-threading, there's no networking, there's no decoupling of the rendering from the game update loop and all that kind of stuff. We're sticking to a pretty basic architecture, but you will find that pretty much any 2D game that you want to make, this will be completely adequate for that, and it will be as efficient as you want it to, right? We're talking probably thousands of frames per second. You know, it's very simple 2D stuff, so it'll run pretty quick. What is a component? So we're talking about components that are just pure data. There might be, we might cheat just a little bit where we have a little bit of logic in the constructor of a component, but I'm not going to be doing a bunch of things like, you know, implementing gravity or implementing the input stuff within a component itself. And we'll see that in a bit. I'll have some examples of components. So a component class is going to have some intuitive language meaning to it, right? So for example, the position component, you can probably guess what that does. The gravity component, the health component, they're pretty easy to see what they do. And that's what we want to do. We want to design a system such that it's easy to program, it's intuitive, and easy to use. How will we implement these in C++? Well, I have a bunch of examples that I'll show in a few slides. So an entity, again, any object in the game, it has no unique functionality, right? So we're not putting any of these mechanics on the entity itself. So if you were to do something like object-oriented, like pure object-oriented programming, where I might have an entity class, then an enemy class that inherits from that, and then maybe a skeleton, you know, like a skeleton with a sword class or something like that, then inside that skeleton with a sword class, you might have an attack function that overrides the base attack function. And, you know, when someone got within range, it would swing or something like that. None of that type of functionality is going to be on the entity class itself. Instead, we are going to have those systems that implement all of that logic by reading which components this entity has and then deciding what to do based on that component. So an entity really is just a class that stores and manages component data. That's it. In practice, that's what it does in the game. And it's going to store at most one of each component type. What does that mean? It means that it won't have two positions, right? It won't have two gravities. It won't have two bounding boxes. If, for example, you might say, okay, but what if we have an item component, right? And then we want the entity to store multiple items in its inventory or something. Well, then what you would have to do is say, okay, an entity has one inventory, and then you have some data structure that stores items, and the inventory itself would be the thing that holds the multiple items. The entity would not ever store more than one of a particular type of component, right? If you did have something where, let's say it has a position, but then it also has some teleporting ability, and you want to go back to the previous position, then you wouldn't say, okay, we have this position here and this position here. You would have separate components for that, right? So you'd have some sort of teleportation component which would store the previous position. So at most one of each component. You had a question?
In the inventory example, would an item be more like an entity than a component?
The
inventory itself is the component?
So the question was, in the inventory example, would an item be like an entity? So that completely depends. I don't think we would want to store entities within components. But what you would do is you would store data that would be able to create an item entity, right? So you might store some sort of type. Maybe you have a string, like this is a sword, it's worth this amount of gold. Maybe it has this quality, right? And then if you wanted to say, drop it on the ground, and then create an entity so you can see a sword on the ground, then that entity would have some of that data used to construct the entity to create its sprite, to create its position, its velocity, stuff like that. So we would not want to have this situation necessarily where you had entities stored within entities. Now, if it comes down to it where maybe, let's say, one entity might be tracking another entity, like a homing missile or something, you might want to store some sort of reference to an entity that it's actually tracking. But what we would want to do there is eventually we'll see that entities are going to have unique integer IDs associated with them. So instead of storing like a full entity and all of its data within an entity, we'd probably just store the ID of that entity and then go look it up later when we want to. Another question? No, that would still be, so the question was, what if you had fewer levels of hierarchy in the object-oriented example? I would still say if you're using that sort of inheritance, and instead of, so you have entity, and then you have dynamic and static, but instead of that, maybe you just like have all of your different entity types, then well, if you don't have components that you can attach and detach, then it's not ECS, right? It's still object-oriented. But yes, well, there might be things that are common to them, but there's a big difference between I have a class which has a velocity in it, and I have an entity class which stores components, and one of them happens to be a velocity, right? Because there's a system there for storing components. We'll see a few more examples. This will become more clear, hopefully. How components are stored and used within an entity can be a complex topic, and I'll go over a few of those options now, and hopefully that'll sort of clear up that question. So how we actually implement these things, that's an important design and programming choice. So since there will be at most one of each component, the first and most obvious option might be just store a variable for each type of component that we have, right? So if I can only have at most one of them, then I'll either have 0 of them or 1 of them. So just have one variable for each component type. If I have 10 different types of components, then have 10 different variables in the entity class. That could work. We'll see that in a sec. Or what we can do is, if we don't want to explicitly have one variable for each component type, then we could store a single collection of components, right? So this is a more generic, more abstract way. And then we could use functions on the entity class, sort of like add component or get component, for more generality rather than having to know exactly what the variables are and stuff. So let's have a look at some concrete examples. Here's that first example where I have an entity class, and I'm just going to make everything public here so that I can access them directly. And so if I have a component, so here my naming structure for these components is just a capital C, meaning component, and then the name of the type of the component. So this is a perfectly valid way to store components. Let's say I just have 4 different components. I have a transform, I have a name, I have a shape, and a bounding box. That's it, right? So let's see how we might use something like this then. So here's some sample code of using this entity. So I could say, okay, e.cTransform equals cTransform vec2 100, 200. So this might say position my entity at 100, 200 within the world. Just by creating a new instance of this class. Now we have name, let's say this is a red box, and we have a shape, which is, okay, I'm going to construct a shape with some arguments. Maybe it's a rectangle, maybe it's a circle, etc. But if we look here, this also had a bounding box, so our entity class stores one of each component, no matter what, because I can't take variables out of a class or add variables to a class, at least in an easy way. So we do have this entity that does not have a bounding box, right? So if these are all just default constructed stack variables here, how would I tell which components actually exist within this thing? Because it has the variable, and so we would need some way of saying, okay, if e.cTransform.exists. So in this case, what we would need, in order to tell whether or not the entity actually has this type of component added to it, like explicitly added to it, our component would need to have an extra variable to say whether or not it exists, right? Now the class, the instance, the member variable literally does always exist. But what we're trying to say is, have we actually added this thing to the entity in terms of the game mechanics we want to implement? So in this case, what we would have to do is just say, okay, each of these components is going to have a Boolean inside it, which is called like exists. And if this, the default constructor would say false, it does not exist. And then when we explicitly construct it with a non-default constructor, we would say whatever dot true. And so the good thing about this is it's memory safe, right? We don't need to worry about any memory leaks here or freeing or deleting anything. It's contiguous memory, meaning that all these things are going to live right next to each other in memory, which is good. That's good for cache coherency. There's no heap usage. So if you watch a C++ lecture, we want to avoid using the heap whenever we can. These dynamic memory allocations are pretty slow. And so those are all good things. So whenever I list a good thing, it's going to be in green. Whenever I list a bad thing, it's going to be in red. One of the things here is that directly accessing the member variables is not something that's really desirable, right? Why is it not desirable? Well, first, it's unsafe, because any system that has access to these entities could just directly access the variables and, like, you know, change the properties in ways that we may not be able to expect, etc. So that's not great. But also because we really want to, wherever possible, decouple the ideas and architecture of how these components are being stored with the logic of our game mechanic systems. Like, for example, let's say we did implement our system like this, our entities like this. And then later on, some really smart programmer comes and says, okay, I found a better way of storing all of these component data. Well, now what you're going to have to do is change all of your code that ever interacts with an entity. Why? Because all of your code is going to be directly accessing the variables of the entity class like this. You may have tens of thousands of lines of code that interact with these entities. But you've got to change all that if you change the way that these entities are stored. And ideally, whenever you program, and I will stick to this till the day I die as a lesson in programming, wherever you have logic that is taking data and transforming it and performing some sort of calculation, like a game physics system or something like that, that should not need to know how the data is being stored. It shouldn't need to know whether or not these are pointers or stack variables or stored in a memory pool, or, you know, they're coming from a network or whatever. You want to decouple those as much as possible, and I'll show how to do that in a bit. Another bad thing is that this entity contains, you know, this exists thing that we just did. It requires another variable, which is a little bit annoying, and you also have to check this variable, which is super annoying. Like, you have to know that that exists variable is there, and you have to call it every time. And what if we want to rename that variable? Because maybe someone doesn't like exists. Maybe they want to change it to contains or something like that, right? It's kind of annoying. So there are some, even though this is great because it's memory safe, it's contiguous memory, it's no heap usage, it has these other software engineering properties that we don't necessarily like. Okay, so let's see what would happen if instead of using just stack variables, we instead use raw pointers. Let's go crazy and use raw pointers, right? So what we would do is we would have an entity, and all of these pointers to these classes initially would all be null pointer, right? Because they don't exist yet. We haven't added anything to this entity. One of the immediate downsides of this is that now what we have to do is, in our destructor of this class, we have to explicitly free the memory or delete the classes that we have. So we would have to go through in the destructor and say, okay, if I have a transform component, then delete that transform component. If I have a name component, delete that. So that's a little bit annoying, right? We would want this, this over here doesn't need a destructor, because all of those classes will all destruct themselves when it goes out of scope, but over here we would need one. And so instead of just being able to say e.cTransform equals cTransform, when we're using raw pointers, we need to have this new keyword, right? So new is going to allocate things on the heap. Oh God, now we're using the heap, that's bad. But the one thing that is better is that if we want to check to see if that entity has a particular component, all we need to do is say if e.cTransform. Why? Because if it's null pointer, then that will be false, and we know that it doesn't have it, right? So we no longer need this extra variable to see if this particular component exists within the entity, because that's sort of handled for us by the fact that, hey, it's just going to be null pointer, which is equivalent to 0, essentially, if it doesn't have it. So that's a little bit nice. So the entity contains component check is slightly easier, maybe a little bit more intuitive. However, there's memory leaks here, right? Because what if later on I wanted to change the shape of this entity? Well, what I would need to do is, if I don't check to see, okay, if it has a shape already, then I need to delete that shape to free the memory and then create a new one. And we don't want to be worrying about memory management in the middle of our logic code, right? That's the last thing we ever want to do. So if we don't deal with that, it's a memory leak, so we have to check and delete things. It makes it really cumbersome and unsafe. I would not recommend using this for any reason. It also uses heap memory, so it makes it quite slow, which is annoying. And again, we have this direct variable access, which we don't want to do for the exact same reasons that we did before, but it's even worse now because we have direct access to those pointers, which could point to anything in memory and have null pointer exceptions and all sorts of stuff. So yeah, we don't want to do this. But maybe we still want to use pointers, right? But not raw pointers. So let's say if we use like a shared pointer or a unique pointer. So we're going to use a smart pointer instead. So this would be the syntax for that. And over here, instead of saying new, we would use make shared, or you would have the constructor for a shared pointer for that syntax, and we would say, oh, I got a little typo here. So the transform would be standard make shared C transform with those arguments, etc. And we can still use this nice syntax of telling whether or not a component actually exists, because it's still a pointer and we can check if it's null or not. Okay, so that part is a little bit good, but it's better than the previous one because this is now memory safe, right? This implements RAII that we talked about in the C++ lecture, and so I can overwrite these, no problem, and the previous one will just clean up itself because it implements RAII. So that's good. It's memory safe now because these smart pointers implement RAII. The entity contains check is still easy. So this is a little better than using the raw pointers, but it is slower than raw pointers because smart pointers do have a little bit of overhead where they check their internal reference counters and stuff. And so smart pointers are a little bit slower. It's still slow due to heap usage. It's a longer syntax, so it's a kind of a pain to type that every time. Yes, we could make some sort of function that sort of handles that for us if we wanted to, but it still allows direct memory access as well, and so we wouldn't necessarily want to do something like this. Now, in previous offerings of the course, what I did was I said, all right, in assignment 2, we're just going to use this one. We're going to use this system where we have one variable for each component, and they'll be shared pointers. And I said, we'll improve it later. But this year I decided, no, let's just show you the better way of doing it right away, rather than having one assignment that's different than the others. The next way we could think about, so the fourth different way, is to have some sort of component container, right? So this seems reasonable. I'm going to have a vector of components. That's going to be my M components here. And then I'll have functions like, I want to add a type of component to this. I want to get a type of component from this. And so this ends up being a little bit slow in practice due to implementation details, because you can't simply store, even though if we had, for example, a component base class that all of our component derived classes inherited from, we could store all the components like this. But then what we have to do is we actually have to store a pointer to the base component class, because you can't do inheritance with raw. I think I talked about that a bit in the C++ lecture, but the implementation details of this are kind of bad, and it ends up actually being slower to implement than the next thing I'm going to talk about, because what we have to do is we have to find, okay, which C++ doesn't have anything like reflection that lets us just immediately tell what type of class something is. You have to do casting and checking if the result of the dynamic cast is equal to null and all sorts of weird stuff. So let's just say that this is bad without going into all of the details, and we won't necessarily want to do it like this. But what it would look like, the good thing about this is that the syntax is now very generic, right? So we have this private vector of components. So we have this information hiding that I really like about object-oriented programming, and we have these functions that let us get access to that in sort of generic ways, right? So to the user of this, the user of this component container has no idea how that data is stored, and it doesn't have direct access to the member variables. So those are the good things about this, right? Is that I can just say, add a component of a particular type and pass in the constructor variables. add a name, add a shape. It has no idea how that's stored. That could be stored literally any sort of way, and the user doesn't need to care about it. So if later on, if I was using a system like this, and later on I found a better way of doing it, I could change how the components are being stored, and none of this code would have to change. So that's a really good thing. We want to make sure that that can happen, because later on, if you optimize something, you don't want all the code that uses that something to have to change. So the good thing here is that it abstracts away the storage of the component. We don't need to know any of those details. It allows storage changes without usage code changes. Usage code meaning, the code outside of the entity that actually uses the entity. The good thing here is that components are stored contiguously in memory if you can figure out how to do it without using inheritance, which is a huge pain. But if you do use inheritance and you have pointers here, then those things are no longer guaranteed to be contiguous in memory. So that's not good. This is the least amount of code to type, which is really nice. It's less code than before. So we would want to, this is a good way of, this is a good API or a good interface into the entity class. But the implementation of how to do that is a little bit annoying. Luckily, C++, just straight out of the box, I think this is C++ 17 or later, that has this standard tuple. But I can just store a collection of different types of components, just directly. This doesn't have to be in a container with all of, in a vector with all of those weird access functions and, how do I store, where is my transform component in that vector? I'm not sure, maybe I have to iterate through it, etc. This is actually a really cool way to do it, and I'll show you some implementation details of how that works a little bit later. But what we would have now in our entity is I would be able to add a component of a particular type and put in its arguments. I'd be able to get a component of a particular type. I'd be able to check whether or not this component exists, and maybe remove a component as well, right? So this is much faster in practice than the vector-based one, just because of the way that you would have to implement the vector-based one in C++. So over here, this has the exact same usage syntax. See how cool that is? Like, we've implemented a completely different way, but the code of how to use it is completely the same. So that's really neat. Again, it abstracts away the component storage details. It allows storage changes without having code changes. The tuple is on the stack, so that's good. These things are probably going to be contiguous in memory, but I looked up last night, the C++ standard does not guarantee that these things are contiguous in memory. But it is very likely that if you're using, primitive or raw data types that we're going to be using for these components, it's likely that they'll be very close together in memory, which is nice. That's what we want. And again, this is the same least amount of code to type. So this is our entity as we see it right now. I have removed the has and remove functions here just because I couldn't fit it all into a reasonable font size. But all those functions that we had before are still there. Do you have a question?
Yeah, I was wondering, why is it still beneficial for your components to be close to each other in memory if you can't guarantee they'll be adjacent?
Because of cache coherency, essentially, right? They're all going to be living in this tuple object. It just says that it's not guaranteed for them to be contiguous in that order. So for example, if you have C++ and some, I don't want to go into too many details right now because I have a whole other lecture on it, but there's things like packing that can be done. Like if you have a 1-byte data structure, like a bool, followed by a 4-byte data structure, C++ likes to store things in 4-byte chunks. And so you may actually get like 3 bytes of null padding or something like that happens. And so there's just nothing that says it's guaranteed to be these 4 bytes, these 4 bytes, these 4 bytes, these 4 bytes. But if it's some combination of that or close to that, then if I look up the transform component and for free in my cache, now I also have the name component, that would be nice if possible, right? And let's sort of forget about that for now, because later on we'll show how cache coherency is all about access patterns. And it turns out our access patterns, we're going to want to do something else if we wanted to be maximally efficient and not actually store the components inside our entities whatsoever. So that's like lecture number 18. So I don't want to, I hate glossing over the details, but it's not really the depth I want to go to in this particular lecture on that. So hopefully they're closer together, they're usually contiguous, but the standard just doesn't guarantee that they're contiguous. That's all I wanted to mention there. So here is our entity class so far. We've got our components, and we've got some functions that allow us to get at those components. But we're going to want some other functionality on the entities that are not components, that are just like software engineering type things. And those are the following. We're going to have 3 more variables. One of them is a bool, which is alive. Is this thing alive? What that means is that the entity should still exist on the next frame. So for example, the way that we'll end up killing entities is we're just going to set this variable to false, and then our entity manager will do a loop over all of our entities and remove all of the ones where this is set to false. But we'll talk about a lot more of that in the next lecture. Also, something that's nice to have is a tag, some sort of description of this entity, right? So for example, if I make a bullet, I could tag that with bullet. I can tag the player with player. I can tag the tiles with tile. And then in our entity manager, we're going to have a little data structure in there that lets us do something like say, get all the bullets, get all the tiles, get all the Koopas in the Mario game, right? So this tag is going to allow us to be able to get types of entity collections really easily. Now, I will say right up front, because I always get this question, no, storing a string like this is not the most efficient way of doing it. But it is a completely abstract, arbitrary way of doing it so that what we don't have to do, for example, if you wanted to be maximally efficient, you would create an integer enum and list every possible entity type that you could have in your game. So you would say, okay, bullet is entity type 0, player is entity type 1, tile is entity type 2, and then here you would just store an integer enum corresponding to that int. But again, this is just a balance of usability, right, and learnability and efficiency. We will talk about changing that a bit later, but for now, we're just going to have this string here because it's fine, right? It just works. And also, every entity is going to have a unique integer identifier associated with that entity. So for example, if we have 2 tiles in the map, or we have 2 bullets, they may have all the same properties, but we may want to check to see, even if they have all the same properties, are these literally the same entity? Meaning, are they the same object, right? In programming terms. And so we'll have this ID here. Whenever we create a new entity, we're just going to give it like the next integer. So the first entity we create is entity number 0. The next one is 1, 2, 3, 4, up to however many entities we want to create. And so that's just something that we'll be able to use to check to see, is this entity literally equal to this other entity? And then we'll also have some functions associated with those. So we do not want direct memory, direct variable access to these. So we have some getter functions down here where you can get the ID, you can check to see if it's alive, you can destroy the entity, or you can get the tag. So this is essentially what our entity class is going to be. It's all of the components, a unique integer identifier, something that says whether or not it's still alive, and then a tag that we can use to describe the entity or give it a type somehow. Up here you see I've got a standard tuple of one component, another component, another component, another component. We may have a dozen or more components by the time you get to the project. And so here is a convenient syntax in C++, is we can say define a new type that is equivalent to some type that we don't want to type out all the time, right? So if we have a standard tuple of transform component, lifespan component, input component, bounding box component, all these different types of components, I can say using component tuple equals the standard tuple of all my components. Now what I can do is where I had this before, where I defined this huge variable name, now I can just call that a component tuple. Right? I didn't have to define a new class that stored all that. I can just say using component tuple equals this. You may also have seen this as a type def. So you can type def standard tuple blah, blah, blah as this other thing, which is essentially just a macro for saying whenever I type this, I actually mean this other thing. It's just that using is sort of the more modern C++ syntax for doing that. So that's what that does here. So if you ever see a component tuple, that is just a standard tuple of all of our different component types. Some quick notes on using a standard tuple. So if we want to declare a standard tuple of various types, this is how we do it. Standard tuple, int, double, int, float, size t. I can have any number of different types within that tuple. Okay, how do I get access to things in that tuple? If a type is in the component exactly once, I can do this syntax where I say standard get the type. Up here you can see there's only one double in this tuple. So if I say standard get double and then call the variable my tuple, it knows exactly how to get that, right? So this is how I would set that variable here, standard get double my tuple. But let's say, for example, I want to get access to that second integer. If I say standard get int, I don't actually know what will happen because it can't get it because there's two different ints, so it doesn't know which one to return. So you can also use an integer index into this tuple to get that if you want to. So if I want to get this exact int variable, I can say standard get 2 because index 0, index 1, index 2, that's how I would get that int. We're not going to be using this integer referencing in our actual code, but I just wanted to show you how you would if you did. And if you want to, if you want to set variables or just get variables to use them somehow, you would use that same syntax. And you can also have an initializer which initializes variables as you declare the tuple, which is really nice, so you can put different types into this. And the really cool thing is that since our entities, we have designed it so that each entity is going to have at most one of each component, then we will be storing a tuple of unique types. So I can just use standard get and then the type of my component to get the type from the tuple. So I don't have to worry about, like, if I had used a standard vector, which index is my whatever component living in, we can just use standard get. And under the hood, it does all this in constant time. There's no overhead. It just does all the storage for you. So inside our entity, so get would return a reference to a type of component. So this is how you use templates in C++. I went over a bit about that in the lecture. So this function get is templated on a type name called t. So this t would be a transform component or a shape component or whatever, right? So I would call get and then, well, the same syntax we've been using. And it would return standard get, the type, called on my component tuple. So it couldn't be simpler than one line of code that returns it, right? Now, this returns a modifiable reference type, but sometimes we want to follow const correctness and also have a const version of that. So we would have a const version of get and a non-const version of get, and we will see in the future why this is so important to have a const and a non-const version when we have accessor variables like this. So that's how we would implement get. Pretty simple. How would we implement the has function? So how do I say, okay, does this have this? Well, what we're going to do is we're going to have, and I'll show this in a couple of slides, a base class of component. The base class of component is going to have this exists variable. The default constructor is going to set this to false, and whenever I add a component, I'm going to set that to true. So when I explicitly add a component, I'm going to set that to true. And so I check that. So the outside code just says, does this have a transform component? It doesn't need to know that this, this exists variable is here, or that components are actually inheriting from this base class or whatever. If I want to remove a component, all I have to do is get that component and then set it equal to a default constructed component of the same type. And that resets that entire component, sets the exists back to false. Couldn't be easier. The most complex one is when I want to actually add a component. So when I go back and I want to, let's see here, add a component. So I had some code here. So I want to be able to say entity.add, and then the template argument is the type, and then just directly pass in its arguments. C++ lets us do that, And here's the way that we do it. Don't worry if you don't memorize all this syntax, it's fine. But our template for this function is going to take in not only the type name, t, but also this type name ... targs. That's a way of doing forwarding of arguments. So it allows us to pass in an arbitrary number of function parameters equal to the constructor of whatever type that we're passing in. So we can just directly pass in the same parameters we would use as if we were going to construct it, rather than having to construct a component and then pass that in explicitly. So we would say auto component equals get of the type. So we've gotten a reference to that. And then component, which is now that reference to this, we can say, okay, call the constructor of that type and forward the arguments that we passed into the add function. So this is just a little bit of modern C++ syntax sugar to allow us to forward those arguments, and it can be arbitrary. If one type takes in no arguments and another type takes in 6 arguments, this one function will be able to forward any number of those arguments for us. And then since we are explicitly adding this component, I am going to say that the exist variable on that component is equal to true, and then I'll return a reference to that component. Okay? So the component default constructor has this, this is supposed to be exists. That is set to false by default, and it's only set to true when we explicitly add a component. And if we remove a component, again, it default constructs it, and so that exists variable is set back to false. So that's how we're gonna do things. Okay, this is how the entity is going to be implemented. How do we implement the components themselves? We're going to have a different component class for each component that we want to implement. That's pretty basic. So the naming convention that we're going to use is C followed by the component name. Components are going to inherit from a base component class, which stores any data that we want every component to have. Let's say, for example, later on, we say, I want to know how long or how many frames a particular component has been attached to an entity. Then, okay, I can actually store in the base class, like some attached 4 frames or the frame that I attach this, so I can, do more bookkeeping if I want to. But for now, what we're going to do is the base class component is just going to have this exists Boolean. And so every single component now gets this variable that we can get and set for free. So exists is whether or not the entity actually contains that derived component. And by default, it's set to false, so that if we haven't explicitly added it, we don't think it's there. Here's an example of a component. I think this is exactly what we're going to be using in assignment 2. This is our class C transform. So in computer graphics, a transform is essentially anything that takes data and moves it or rotates it or scales it, etc. So our transform component is going to be our most important component that stores things like the position and the velocity. So we'll have this vec2, which I'll talk about in a little bit. This is essentially just an x and a y with some extra functionality on it. We'll have a default constructor down here that does nothing, and we will have a constructor that takes in a vec2 position and a velocity and sets those internal variables. So that's just an example. That's what the transform component is. It stores like the physical properties of the component in our world. Then we might have a shape. And so, for example, this component shape might store a circle shape, an SF circle shape, which stores things like its position, its size, its radius, its color, all those things. We may have a lifespan component. So picture, if you will, wanting to be able to attach a component to an entity that says after 180 frames, so 3 seconds, I want this entity to just disappear. So we would have this lifespan component here. So we would say, okay, here's the total lifespan that this thing had, and here is the current amount of lifespan that's remaining on this entity. And then when I pass in the total lifespan, that gets set to the total lifespan as well as the remaining lifespan. So for example, if I had a lifespan component with 180 frames, then this total lifespan would always read 180. So I can reference that if I want to. And then every frame, I'm going to have a system which decrements that by 1. So halfway through, this is going to read 180 and this is going to read 90. And then whenever we reach 0, I know that I'm safe to delete that entity because something said, I want this to be deleted after so many frames. So now that we've said that, how do we use entities? Well, it's pretty easy. Let's say we have some collection, maybe just a vector. Oh, you had a question?
Could you please go back to the shape component?
Yep. Yep, no worries. So how do we use entities? Let's say we have a function, and that function takes in some collection of entities. So a reference to a vector of entities here, for example. I can iterate through those entities and do something like, hey, add the velocity to the position. Take the shape of the entity's shape component and set its position to the transform's position. And then window.draw e.shape.shape. So I know .shape.shape is weird, but it would essentially get the shape component and get the shape variable from the shape component and then just draw that to the screen. So you can see how easy it is to use this now. It's just as easy as anything else, even though we have all these components. Oops, I didn't use our new syntax here. This is supposed to say .get C transform. So apologies, I didn't change that slide. So just pretend wherever I'm referencing these as variables, I actually put the .get syntax in there. Apologies for that. The following slides are going to use that same old syntax, which I didn't mean. So here, this would be our movement system. Our movement system just says, hey, for each entity, add the velocity to the position. So these systems, pretty much every entity is going to have at least a transform component, right? Because it has to have a position, a velocity, etc. But maybe it doesn't. Maybe one doesn't have a transform. So some systems only operate on entities which contain certain components. So for example, a movement system would only operate on things that have transform components because they have to have a position and a speed to be able to move, right? Rendering would have to have a transform and a shape. Physics would have to have a bounding box. And so we can filter out entities before passing them into our system, or we could just check entities that are required for, check the components during sorry, gotta rephrase this. So in order to filter out the entities, we can just use the has function to check to see if an entity has a particular component in the system that we're trying to do it for. And so I have an example of that, which may make this a little bit easier to understand. So here, for example, this is actually like solution code to assignment 2. So the lifespan system. What does a lifespan system do? Well, it goes through our entity manager. That'll be the next lecture. So this gets all of our entities, stores it as variable e, and then I say, okay, if this entity does not have a lifespan component, continue, go to the next one. So the lifespan system is only going to want to operate on entities that have lifespan, right? So rather than say if it has lifespan and then make like a bunch of nested loops, what I like to do is actually eliminate cases and then operate on things that have the property. So, okay, the following code will only happen if it has a lifespan, because if it didn't, it would have gone to the next one. So I'm going to get the lifespan dot remaining lifespan and minus minus. So I'm going to decrement that. So if it was at 100, now it's at 99. So this lifespan system is going to be called every frame. Then it's going to say, look at the lifespan remaining, and if it's less than or equal to 0, destroy that entity. So this is the entire lifespan. So we've just implemented a system where I can attach a lifespan to any entity for any amount of time, and then this system will go through and decrement that and then destroy it when necessary. So, if I have an explosion animation and I only want that to live for 1 second, I can just attach this lifespan and it'll just handle it for me. Here's another one, which is maybe the rendering system. So I can say something like, if the entity has a shape and it has a transform, then set the shape's position to the transform and then draw the shape. So that's how I would use that, right? Just to filter out things that that have the properties that I want. So here's a little diagram. This is not necessarily exactly what we're doing in our system, but I shamelessly took this from somewhere. So our entities have components. So for example, a size, a gravity, a position. Then we can do things like say, if the entity, we loop over all of our entities, if the entity has gravity, then pass this into the gravity system, right? Update the coordinates and then pass it into the next system, etc. So this is what it's going to look like. Our entities are just storage containers. They're clever storage containers for getting access and adding, or getting access to components and adding components. And then the systems are the things that do all of the logic. Okay, now I'm going to talk a little bit about this vec2 class. The vec2 class is going to be very useful for everything that we're doing in class. So vectors in games, for 2D games and for 3D games, but we're only really talking about 2D games in this course, many quantities and properties have both an x and a y coordinate, right? So, 2D, going to have x going horizontally, y going vertically, and these form a 2D vector. So this vector here is a mathematical vector from like linear algebra, not a standard vector that you use to store things in programming. They just unfortunately have the same name. So for example, we're going to have a position, which contains an xy, and a velocity, which contains an xy. And it's really annoying to have to store two of each variable. You wouldn't want to say like, okay, a velocity x variable and a velocity y variable, a position x variable, a position y variable. That gets a little cumbersome. So we're going to make a class called vec2, and this vec2 is essentially just going to store an x and a y for us. So we're going to go a lot more in depth on some vector math later in the course, but first we're going to introduce the programming architecture that we're going to use for that, and later use that architecture to implement the game math and the physics context. And just as a quick note, SFML comes with its own vec2 class, right? So in reality, you may not want to create your own vec2 class, but I want you to get used to this, or I want us to make our own custom vec2 class so we can look at the C++ implementation details of it, things like operator overloading, chaining, stuff like this, so we can actually see how it's done rather than just telling you, hey, this already exists, let's just use it. We're going to be kind of reinventing that class for this course. So when designing this course, we first have to ask, what variables do we want to store in this? That's pretty obvious here. It's just an x and a y. What do we want to do with those values? Well, we're going to need to get access to them. And for classes like this, I just talked about things like, data encapsulation and object-oriented programming, where we want to make variables private and have members and getters and whatever. But sometimes for such very simple classes like a vec2, we just want to have like public access to that x and y. So we can just call .x and .y without having to call other functions. So we're going to have some functions and operations on that. And so some possible operations that we might want is maybe we want to add two vec2s together. Maybe we want to subtract them, divide them, multiply them, call some functions on them. What is the length of that vector? Maybe I want to normalize that vector or rotate that vector or something, right? So this is why we're going to create our own class. So here is the vec2 class, or it's a trimmed down version of this. Our actual version that we use for assignment 2 is going to have a few more functions that you'll have to implement. So we're going to have this vec2 is going to be storing floats. So we're going to have an x and a y. Default constructor is just going to set them to 0. So we have a default constructor here. We also have a constructor that takes some inputs. So I'm going to want to be able to construct this with a given x and y. And then I'm going to have some operators. So for example, I'm going to want to tell if this vector is equal to another one. So that might just check the x and the y. I'm going to want to be able to add two vectors together and return the resulting vector from that. Maybe multiply two of them together or add something to this vector. And then how would that actually look in practice in terms of usage? Well, now I can do cool things like this, where I say the position, I'm going to set that up as 100, 200 with the constructor. I'll have a velocity and acceleration, and then maybe, some stupid loop like this just to show you how it works. I'm going to add the velocity to the position, and I'm going to add the acceleration to the velocity. Maybe down here somewhere, I'm going to want to get the length of the velocity, because the length of the velocity is equal to the speed, right? So the scalar speed, or the distance traveled per frame, etc. So these are the types of things that we're going to be able to do with that vec2 vector. And I'm going to very quickly do just a couple of minutes of live coding. I tried for like 20 minutes to change the color of this console to a light mode, and I couldn't figure out how. So you're stuck with dark mode for this live programming just for a bit. And in the last time I gave this lecture, I spent 20 minutes less talking about entities, but I put in a bunch more examples. I made the lecture better. So I don't have as much time for this, but I just want to show you what you will be doing on assignment 2. So for example here, I'm going to have class vec2. So I'm going to create a class. Our class needs to have a semicolon after it. Down here, I have a main function, which is going to end up using this. So here I'm going to have, I'm just going to type in some of that code that I had. So I'll have public float x equals 0, y equals 0. And then down here, what am I going to want? Well, I'm going to have a default constructor. And I'm going to have, I'm not using almond syntax for some of this here just because I want to leave a bunch of it on the screen. So, you know, I'm not putting those brackets on the next line just because I want it to take up less space. We're going to have another constructor where, okay, I'm going to want to pass in a float for x and y. And then this, we are going to use our initializer list. Remember that? So x is equal to x in and y is equal to y in. So there is our constructors. So those are pretty much the only constructors that I would want here, I think. What else do I have? Okay, so down here now what I can do is I can say vec2 v1 and give that 100, 200, and maybe vec2 v2, and I'll give this 500, 500, we'll say. And then standard cout v1.x, oops, and then v1.y. All right, let's see if this compiles and runs. Okay, so that's all that I can do with this right now is just create 2 vectors. Let's say that I would want to be able to add 2 vectors together. So if I want to be able to add 2 vectors together, there's 2 ways that I could do that. One is to say I want to add a vector to this one and have its internal variables change, right? So I could say for that one, I would have void because I don't necessarily want to return anything for this. Void add, and then I can say vec2, or I'm going to say just for const correctness, const vec2 reference, and this is going to be another vector. So this is going to be v. And then how do I implement that? Well, I'm going to say x plus equals v.x and y plus equals v.y. Down here, what I can do then is say, let's have a v3, or let's say v1.add v2. And now if I run it, if I've done things correctly, I've taken v2 and added it directly to v1. Okay, that seems pretty easy. But what if I wanted to say something like this? Vec2 v3 equals v1 plus v2. This is very convenient to be able to say, right? But currently, I cannot do that because, well, let's see what happens. If I try and compile it, it says invalid operands to binary expression v1 and v2, so it's 2 v2s. So what I have to do here is I have to actually go add that operator. So this operator is going to return a newly constructed vec2, and it's the way I declare that is with operator. That operator is going to be plus, and this operator is going to take in a const vec2, and this RHS, that just means right-hand side. Okay, so that's the right-hand side of this operand. And down here, I can say return a new vec2, which is x, which is the current member variable, plus RHS.x, and y plus RHS.y. Now, if I compile and run, okay, but what I have to do now is come down here and actually print out v3. It should print out the same thing, but essentially I've added v1 and v2 together. Oh, and the reason for that is because I've added v2 to v1 and then added them both together. So that's why I get this much larger value. So let me just take out this line so that it becomes a little bit more intuitive. right? Now I get 600, 700 as expected. What else could I do here? I could also add something else which scales the values. So vec2 operator multiply, and then yes, I could multiply by another vector, but I want to show you a different one where I have a float scale. And so what this does is it takes in that value and multiplies x and y by that value. Okay, so what's that going to do? Down here, I can say v3 equals v1 plus v2 times 2. See if that works. Oh. Non-void function does not return a value. Oh yeah, did I do that? This function would directly modify the values, but I made a mistake here. What I have to redo is return a new vec2, which is x times scale and y times scale. That's what I actually meant to do here. Oops. Nobody caught that. Everyone was sleeping. So here we go. So now I can take the result of that, which is another vec2, and then multiply it by something. So this is cool. Something else that I could do here is have a function which is like length, right? And so length of a vector, this would just be Pythagorean theorem to get the length of something. I'm not going to type that in for you because that's part of assignment 2, so I'm going to let you do that. But something that I do want to show you, which is pretty neat with the 1 minute that I have left, is this, which is a concept called chaining, which is really interesting. So let's, up here, let's have one more function that does something like this. So this add is here. I'm going to do scale. And this is going to take in a float. And what this is going to do is that this is going to scale it in place, right? So this will be multiplied by s, and this will be multiplied by s. Okay, so that will take that variable and scale it. So what we have there is, let's say we have, let's say I have my v1 and I want to add something to it. So v1.add, and I'm going to add v2, and then I want to scale it. So v1.scale by 5, right? So this is just 2 commands. That's what I've written. And I'm going to print out v1 here. So anyone who's paying attention, what should this equal? I'll play the Jeopardy music. Okay, so it's multiplying by 5. That's not easy. So it's 3,000, 3,500. It's just the values that I had before times 5. But what's really cool is, right now, these add and scale functions are void. They don't return anything. What I can do is let's have them return a reference to a vec2. But what vec2 am I going to return a reference to? I'm not creating anything. I'm just modifying myself. So let's return a reference to myself. So this is a pointer referring to myself, and I'm going to dereference that and return it. Okay, why would I want to do that? Well, let's do it to this one down here as well. Now this still compiles and runs exactly like it did before, because I can still call it without using the return variable, which is what I was doing. But if I do call this, watch this, v1.add v2. What is the result of that? It actually returns a reference back to v1. So what I can do now is, since that's a reference still to v1, I can do this. v1.add v2.scale by 5. Same result. But now let's say after scaling it, I want to add something else. Let's add v2 again. And I can chain these things as many times as I want. Some people like this, some people do not like this. I just wanted to show you that using these functions and these operators you can accomplish things like this. That may make some tricky math a little bit easier to do in the rest of the course. That's it, thanks.